Hello, so in this video we are going to continue looking through quadratics, and actually in this video I'm going to really focus on the properties of what a quadratic looks like. So I'm actually going to start with not a quadratic, but with something that you may be familiar with, and if you're not familiar with it yet, you will be by the time we look at the next theme. So I wonder if you could tell me what would the graph y equals x look like. So y equals x. Well, first of all, let's really understand, what is this equation actually telling us? Well, it means that if we were going to graph this, so if we were going to draw this on a graph, where we'd have an x-axis and a y-axis and the origin where those two axes intersect, then it means that find me all of the set of points where the y value is the same as the x value. That's what equals means. It means is the same as, okay? So literally what this equation is telling me, if I want to graph it, it means find me all of the points which have the same y value as the x value, okay? So as an example, the point 1, 1 would work here, okay? Because that has the same y value as it does the x value. The point 2, 2 would work here, because that again has the same y value as it does the x value. In fact, 3, 3 would also be valid because that has the same y value as it does the x value. In fact, I could even go negative. So -1, -1, that would again have the same y value as the x value. And -2, 2 and -3, 3. And hopefully what you realise and what you can see here, in fact 0, 0 would also work as well. What you can see here is that if I join all of the points together which have the same y value as the x value, I would get a line that looks something like this. So in other words, it's a straight line that is at 45 degrees to each axis, and it's got a positive gradient, okay? It's going upwards. In fact, if I come over to Geogebra, then I'll be able to draw this, okay? So I've just come into Geogebra Classic here, and if I just simply plot the graph y equals x, you can see that in black, I've got the graph y equals x here. Now, what if I want to do something with this graph? What if I want to make it look a bit more interesting? Well, let's suppose instead of looking at y equals x, let's suppose we look at something like y equals x plus 1, okay? So y equals x plus 1. Now just think again, what is this actually saying? Well, the y value, so find me all the points which have a y value, which is just simply whatever the x value is plus 1, okay? So just find me all of the points which have the y value, which is the x value plus 1. So for example, if I give you an x value of 2, you should have the y value of 1 more than that, or 3. Or if I give the y value, the x value of -5, then if I add 1 to it, I get my y value of -4. So basically find me all the points which have the y value as the x value plus 1. Well, in fact, instead of just drawing this sort of manually by hand, let's actually come back to Geogebra and actually let's see what this looks like. So let's plot the graph y equals x plus 1. Now you can see, and maybe if I make this a little bit clearer by changing the colours, okay, so let's maybe change the y equals x plus 1 to a green, and let's maybe change the old one to a kind of purpley colour, okay, so hopefully you can see that. So this is y equals x, the one in purple, and this is y equals x plus 1, the one in green. Now hopefully you can see here that all has happened is we've taken this graph here, and we've just simply added 1 to it. So in other words, all of the points have just been moved up by 1. That makes sense, because if you think about it, all we're doing is taking the x value and adding 1 to it to get the y value. And remember, the y value corresponds to the height of the point, so therefore, if we're just adding 1 to whatever the x value was, we're just simply moving the graph up by 1. Now, in actual fact, I can show you this because you can start to think, what happens if instead of adding 1, I want to add like 2, or I want to add 3, or y equals x plus 5, or y equals x plus 1,000,000. Could even do subtraction, like y equals x minus 2, or y equals x minus 3. So let's see what happens then if we change the value which we're adding each time. Let's go y equals x plus some particular value, and I'm just going to call it a for the time being. So let's actually change this to a nice green again. So what green were we using? That one there, I think, or maybe that one. Yeah. Okay, so basically, let's see what happens if I change the value of the thing which I'm adding. So at the moment, I'm just adding 1, but I can change this to add on different values. Ah, you see what's happening? To get from the purple graph to the green graph, the thing which I'm adding effectively just moves the graph up or down. And obviously you can see now that I'm in the negative space, so I'm taking away values from x, and you can see that I've literally just moved this line down. okay? So you can basically see that all that's happening here is that the thing which I'm adding to my original graph, the y equals x plus something or minus something, basically means that I'm just moving the graph up or down, okay? So we've basically just seen that what's happening here is that the thing which I'm adding, okay, so y equals x plus 1, y equals x plus 2, y equals x plus some value, the process of adding something effectively moves the graph up or down. So I'm going to call that a shift vertically, okay? So a vertical shift or shifting vertically. Okay, so that's interesting. So basically if you start with y equals x, and if you then add or subtract something to that graph, you're effectively just moving the graph up or down like so. Okay, fantastic. So now let's take this a little bit further, and instead of just adding or subtracting something from my graph, what if I want to change it so that I'm multiplying by a number instead? So for example, y equals 2x. What is that going to look like? Well, first of all, let's think about what this graph is literally saying. It's saying, find me all the points where the y values are twice the x value. Okay, so if I give you an x value of 4, then I should expect that my y value should be 8. If I give you an x value of negative 2, it should be that my y value is going to be negative 4. So all this graph is literally saying is find me all the points where the y value is double whatever the x value is. Okay. Now again, let's come back to our Geogebra and let's see actually what this would look like. So let's start off by plotting y equals 2x. Okay, so let's start off by plotting y equals 2x. And actually, let's change this to my green again. In fact, no, let's change it to a different color. Let's go for maybe a nice red. Okay, so you can basically see in order to get from the original graph, which remembers y equals x, that's in my purple, and to get to my new graph, which is y equals 2x, you can see that effectively it's just a little bit steeper. Okay, and that makes sense because all of the x values now, you need to double to get the y value. So instead of the original graph where the y value was the same as the x value, you now need to double that x value to get the y value. Okay, and again, let's see what happens if I maybe change the value of the thing which I'm multiplying by. Okay, so let's change this again to a red. And let's see what we get, okay? So let's see what we get. So at the moment, it's just 1. So that's just basically the same as y equals 1 times x. That's the same as y equals x. So therefore, it's the same graph as the purple graph. But let's see what happens if I change the value which I'm multiplying by. Ah, that's kind of interesting, right? So basically what's happening is it's almost getting steeper, right? And let's see what happens if I make the value which I'm multiplying by smaller. And let's make it negative. Ah, that's interesting. So basically it's going downwards instead. So in other words, by changing the value which you're multiplying by, you're effectively changing the steepness of the graph that you originally start off with. Okay, so y equals, let's not make it 2x, let's make it something like bx instead. Let's make it bx instead. Then effectively what's happening here is that there is almost like a steepness. It's changing the steepness of the graph, or the way which we could describe that is it is a stretch. Okay, so a stretch would effectively be making the graph steeper or shallower, okay, depending on the values. Okay, so that's really important. Okay, we've just seen that if we add a number to our original graph, we're making it shift. And if we're multiplying a number to our original graph, we're basically just seeing that it is changing the steepness of the graph. We're stretching it, okay? And of course, you can do combinations of these two things. But my question now is that instead of just starting with y equals x and then either adding a number or multiplying by a number, what would happen if we multiply by another x? Okay, so what would happen if we start off with y equals x? Okay, then effectively we multiply that with another x. Okay, so instead of multiplying it by another number, or instead of adding it by another number, let's see what happens now if we take y equals x and then multiply it by another x. Now, this looks clunky. Okay, have a look at this. We've basically got x and then we've got times x. Now, you notice that when I write the pronumeral x, the variable x, I kind of write it like that. It's almost like two c's back to back, okay? And then when I write multiplication, I actually write it like a cross, okay? But for some people, that's how they write their x's, okay? So if I want to write x times x, for some people, they would write that as x times x. That looks confusing, right? So have a look here. We need to make this look a little bit nicer. So one way that we can make this nicer is using our power notation or an exponent notation. So instead of writing x times x, we've got repeated multiplication there, which you can just basically say take x and multiply it by itself 2 times. In other words, we get ourselves y equals x squared. Okay, fantastic. So now let's actually have a look and see, what does this graph look like? Well, first of all, let's think what it's saying. It's basically saying to get your y value, you should take your x value and square it. In other words, times it by itself. Okay, so just find me all of the points where the y value is just the x value times by itself. That's what I want you to think of as this graph. Now, you may or may not know what this looks like, okay? So let's start off just by drawing ourselves a table of values to let's see what this actually looks like. So I'm going to draw myself a table of values where I have x and then I have y, okay? And I'm just going to draw myself a nice little table here. So let's start off with, say, x from -4 right the way through to 4. So -3, -2, -1, 0, and then 1, 2, 3, and 4. All right, fantastic. Now let's see what the y value we get when we stick our x value in. So just remember, to get our y value, we just need to square it or times the x value by itself. So if we take something easy like 0, okay, so let's start off in the middle. If we take something like 0, and if I square it, well, what is 0 times 0? Well, 0 times 0 is just 0. Anything times 0 is 0. So even if you times it by itself, it's still 0. Now I'm actually going to go right from here. So I'm actually going to look now at 1 and see what the y value is when x equals 1. So if x equals 1, the y value should just be that x value times by itself. Well, what's 1 times 1? It's just 1, right? So that's 1 there. Then if I move to the next x value, if I start with 2, okay? So if I take 2, and if I multiply it by itself to get my y value, 2 times 2, that's 4, okay? Then the next value, 3 times 3, that's 9. The next one, that's 4 times 4, that's 16, okay? So now let's go left, because we filled in most of the table, we filled in over half of it. Now let's look at -1. Well, what should the y value be if x is -1? Well, -1 times -1, well, I know 1 times 1 is 1, so then I just need to think, right, -1 times -1, that's a negative times a negative, that makes a positive. Okay, so any negative times by itself, negative times a negative makes a positive, therefore, that has got to be 1. So -1 squared has got to be 1, not -1. Okay, because remember you've got negative times a negative. All right, let's have a look at the next one. Let's have a look at -2. All right, so -2 times -2. Well, I know 2 times 2 is 4, and then I just think negative times negative, that makes a positive. So it must be positive 4. And let's keep going. So -3 now. Well, -3 times -3, 3 times 3 is 9. Negative times negative, that makes a positive. So that must be positive 9. Then finally, -4, similar kind of thing. 4 times 4 is 16. And negative times a negative makes positive. So that's got to be positive 16. So there we go. There's my table of values. This is what a domain of y equals x squared should look like from -4 through to 4. Okay? So let's actually see this being plotted on a graph. So here we go. I've drawn myself a set of axes, okay? So I've drawn my x values along the bottom there, going from -5 to 5. Reason being, is I've got the x values from -4 to 4, so I want to make sure I can include them. It's good to give me a little bit of space each side. And similarly on the y values, well look, I can see the y values, the maximum y value is like 16, and the minimum y value is 0. So again, I'm just giving myself plenty of space by putting my range along this axis from 0 to 18. That just gives me plenty of space to include it all in. Okay, and then let's just go through and let's actually plot the points in. So all right, I need to go -4, 16 first of all. That's my first value. So -4, 16, that's going to be here, okay? Then my next one is going to be -3, 9. So -3, 9. So that one's going to be there. Oops, not there quite. It's going to be there instead, okay? Then I'm going to have -2, 4. So -2 and 4, that's got to go there. Then -1, 1, so -1, 1's got to be there. Then I'm going to have 0, 0, okay, so that one's going to be there. Then I'm going to have 1, 1, that's the next one, so that's going to go there. Then I'm going to have 2, 4, so 2, 4, that's going to be there. And then 3, 9, that one's going to be there. And then 4 and 16. Okay, good. So now I've got all my values. I just need to join them all together. Now I'm going to join them together with a nice smooth curve. Okay, so let's see how I can do this. Well, I'm just going to break it up first of all. I'm going to draw that one in first, okay? And then I'm going to draw this one in. So let's see how I can do it on this. Okay, It's not bad. I mean, I've just got it off a little bit there. So let me just redo that side again. Let me just make the paper work for me. So let's try that again, shall we? Okay, so there we go. That's not bad. Okay, it's obviously very difficult drawing this on a tablet. Okay, but if you're doing it on paper, hopefully you should have a graph that looks something like this. Now let's have a look at some of the features of this graph. Like, what do we notice about this graph? Well, first of all, have a look down the center line here. So have a look here. I would call that a line of symmetry. Okay, in other words, everything on the left-hand side of that line is exactly the same as what's on the right-hand side. It's a mirror image, okay? If I was going to literally fold it along that line of symmetry, I would get the same graph being imprinted on both sides. There's a line of symmetry in there, okay? Now, we have also discussed what the name of this graph is called, because it comes from something which is squared, y equals x squared, okay? We would call this a parabola. So the type of graph which this we would call is a parabola, okay? But have a look as well. Have a look at the gradient in particular. If you imagine this as almost like a roller coaster. So imagine I'm sitting here, over here on my roller coaster, okay? And I'm sitting in my little roller coaster here. Here I am having a whale of a time on my roller coaster. Can you imagine that over here, this is going to be a really steep gradient, okay? So over here, this gradient is really, really steep, okay? So steep gradient. And then likewise, over on this side, over on this side, there is also a steep gradient over here. So steep gradient. Then if you look at values which are closer to 0, so for example, if I now take this guy, okay, and if I move him down here, can you imagine that when I'm down here, it's not going to be as steep anymore, all right? So in actual fact, this is going to be a shallower gradient, okay, so shallow gradient. And the same thing here, this is also going to be shallow. So what I can basically say, okay, what I can basically say is that as I approach the sort of bottom of my graph, the gradients get shallower. Then as I move away, the gradients get steeper. You happy with that? So as I move in that direction, the gradients get steeper. And as I move in that direction, the gradients get steeper. Now, also have a look at the direction of the gradient, okay? Again, imagine I was in my roller coaster. If I was over here in this part of the graph, I'm facing downwards, okay? You happy? So if I'm on this side of the graph, if I'm on this side of the line of symmetry, I'm effectively facing downwards. Even if I'm over here, I'm still facing downwards. It may be I'm just not facing as downwards as perhaps I was over here, okay? So on this side of the graph, I have a negative gradient, okay? So negative gradient. So everything on the left-hand side, everything on this side is all negative gradient. Whereas if I move to this side of the graph, can you see, if I'm on my roller coaster, I'm now facing upwards, and particularly over here, I'm facing really upwards, okay? So everything on the right-hand side of the graph, I can basically say, I have a positive gradient because I'm facing upwards, okay? Does that make sense? So basically I've got my line of symmetry, everything on the left I have a negative gradient, everything on the right I have a positive gradient, and my gradient is getting steeper the further I move away from the line of symmetry, okay? Now what's really interesting about that is that there must be a really important point, and it's this point here, okay? So this point here. Now this is the point where I'm kind of at the rock bottom of my graph, okay? I'm at the kind of the minimum point of my graph in this case. Now I give this a special name. So this point here is literally where the graph turns. It goes from facing downwards to facing upwards, okay? Imagine I'm on a roller coaster. That's on the left-hand side I'm facing downwards, on the right-hand side I'm facing upwards. So in the middle, I turn. So I would call this a turning point. Okay, I'd call this a turning point. Now in actual fact, we can call it a turning point. A turning point is fine, but there's a better name for it, and a name which perhaps you will come across a lot over the next kind of few weeks. And to give it a name, begins with a V. We call it a vertex. Okay, so the vertex of this graph, of this parabola, would be literally the point which it turns. It goes from a negative gradient to a positive gradient. All right, fine. So just to recap what we've done there, when we started looking at linear graphs, things like y equals x. The reason why we called them linear graphs, so L-I-N-E-A-R, the reason why we called them linear graphs is because they literally result in a straight line. They literally are a straight line. Now, what's really important about this is that they have a constant gradient. In other words, the gradient of the graph, the steepness of the graph, doesn't change at different points, okay? So they have a constant gradient. And we basically looked at how we can change linear graphs to get different types of graphs. So if we add some particular value to our linear graphs, we basically move it up or down. We saw that on Geogebra, right? And also if we multiplied that linear graph by some value, we get a stretch. We make it steeper or we can make it shallower, okay? We then had a look and we said, I wonder what happens if we start with y equals x and then try multiplying it by another value of x. So instead of adding it or subtracting another value, a constant value to it, let's see what happens if we multiply it by another x. Well, we've just seen that when we get that, we can also write that as y equals x squared, we get a completely different shaped graph, okay? We get a graph that looks like this, okay? And what's really important about this is that the gradients change, okay? So as you move further away from the turning point, the gradients get steeper, and that happens on both sides, okay? And also, the gradients move from negative to positive, or positive to negative, depending on which way you look at it. So really, there's a really important point on the graphs, which is called the vertex, okay? And that's just simply the point where the graph turns. Now, interestingly, the turning point is also the vertex, or the turning point, is also the line of symmetry. Okay, so basically if you're going to draw a vertical line through that vertex or that turning point, then you would find the line of symmetry. In other words, everything on the left is the same as what's happening on the right. It's just a mirror image. Okay? So there's two really important features that I want to note about these things called quadratic graphs or parabolas. Okay? So two really important features of parabolas. Remember, parabolas is just simply the shape of the graph which we give when we get a y equals x squared graph like this, okay? So there's two really important features. The first is the curvature. It is the fact that, we no longer have to work with straight lines. We can now work with curved lines. And the way we should do that is just simply by taking x and multiplying it with another x, okay? So we're talking about the curvature graphs now rather than straight linear graphs, okay? But the second important feature, and this is what we're going to investigate now, is that actually we can create an entire family of parabolas, okay? So I can basically now create a family of parabolas, and I can create a family of parabolas in three ways. I can either do a shift, okay? Another word for a shift is a translation, so I'm just literally moving it up or down, okay? So I start off with my original graph, okay? And I can move it up or down. So if I start off with my original graph in blue, okay, I can basically move that graph either up or down. So I can move it up, I can move it down. But are you happy? I can also move it left to right. So I can move it over here, okay, or I could move it over here. Okay, so I can basically move my graph in four different directions: up, down, left, or right, and then I would get a brand new parabola as a result. I can also get a new parabola by doing a stretch, okay? And we've seen that kind of thing happening when we looked at our straight line graphs. So the stretch, so I can either take this graph and really pull it up so it's much skinnier than it was before. Or even I can pull it outwards so it's much fatter than it was before. Okay, so I can get a new graph just by stretching it. Okay, but I can also get a new graph by flipping it. Another word for that is reflecting it. Okay, so for example, if I take this graph and if I flip it around, then I'll get a new graph. So it goes from happy face to sad face. Okay, so basically what I want to do now is look at how I can get a new graph by doing one of these three things. So let's actually start off by talking about our first way that we can transform this parabola to get a new parabola, and that is just by a shift. Now, I know I said I can shift it in four different directions, up and down, and then left and right, but I'm actually going to group those together into two. So I'm going to shift it into a vertical shift and a horizontal shift. Let's look at a vertical shift first of all. So let's come over to Geogebra and let's use that to help us out. So first things first, I'm going to draw the graph y equals x squared. Okay, so y equals x squared there. And I've got that in green. I'm just going to change the color and I'm just going to make that black. Okay, just like so. And in fact, what I might do as well actually is change the style of the line to put it in dotted, okay? Just to show that it is the original graph that we are working with. So there you go. I've got the original graph there on the screen in a black dotted line like so. Now let's see what happens if I can shift it vertically. Well, are you happy that when we were looking with our linear graphs, the way to move a graph up and down was just simply by adding or subtracting a value to it? So let's take, for example, x squared, okay, and let's add or subtract some particular value from it. So you can see now in red that I've got my new graph, okay, and the way that I've moved that graph around is just simply by changing the value that I'm adding. So you can see on the left-hand side of the screen here, that I'm just simply adding or subtracting some particular value. So for example, if I add 3, you can see that the entire graph has been shifted from the dotted graph, that's my y equals x squared, to my red graph, just simply by moving all of the points up by 3. Okay, and again, if I just set this to play, you can see that I'm basically moving the graph up or down just simply by changing the value which I'm adding each time. So just by changing the value that I'm adding or subtracting each time, you can see now we're going negative, so therefore we're moving it down, okay? I can change the sort of shift of the graph vertically just by adding or subtracting some particular value. Okay, fine, fantastic. So let's have a look at that then. So I've basically said, in order to move the graph up or down, I just simply add or subtract some particular value from it. So let's have a look at this. So if I put my y equals x squared, say for example, plus 2 there, okay, that would be, for example, y equals x squared plus 2, or it could be y equals x squared plus 3. I'm just going to do it generally, and I'm going to say that is y equals x squared plus some particular value. So I'm just going to say a, and then we move it a up. Okay, so we've moved the vertex. Look where the vertex has moved. It's moved from the origin, okay, to x equals a. Sorry, y equals a, okay? And if I want to move it down, that is totally fine as well. I could absolutely move it down. So if I want to move it down here, okay, then I would just simply do y equals x squared, but then I'd have to take away some particular value. So that would be down here at negative a. And again, my vertex has moved to 0, negative a, okay? So you notice that's how I move my graph up or down. I move the graph up by adding on some particular value, and I move the graph down by taking away some particular value. All right, fine. So as an example, if I gave you the graph y equals x squared plus 4, just pause for maybe a couple of seconds and just think, where would the vertex of this graph be? Okay, so just think about the transformation that's happened and then think, where would the vertex end up? Well, are you happy that all I'm literally doing here is adding on 4? And we've just seen that if you add on some particular value to y equals x squared, then you're basically just moving it up or down by whatever you add on. So in this case, I'm adding on 4, which means I'm taking that graph and moving it up by 4, okay? So that means then that the vertex of this graph is going to be at 0, 4. Because I've moved the vertex from the origin, moved the entire graph up by 4, which means the vertex also gets moved up by 4 as well. If I take the graph y equals x squared minus 15, then I wonder if you can tell me, what's the transformation that's happened and where would the vertex end up? Well, hopefully you've looked at that and you can think, all I've done here is I've taken y equals x squared and then I've just moved it down by 15. I've taken away 15, so it means I've moved it down by 15, right? So if I'm taking away 15, it means that the vertex will also go down by 15, so it'll end up at 0, negative 15. All right, fantastic. Okay, so if that's a vertical shift, if that's how we move it up or down, what if we want to do a horizontal shift? What if we want to move the graph left or right? Well, I think here it matters what order we add or subtract the value, okay? So we've just seen with the last example that if we square it first, okay, so if we square the value first and then do our adding or subtracting, okay, so if we do y equals x squared, so we square first, then either add a or subtract a, that's how we move the graph up or down. So therefore, in order to get a horizontal shift, I think what we need to do is do it in the other order. In other words, add or subtract the value first, then do the squaring. Okay, so what we want to do is do y equals, we want to add or subtract the value of a first, and then square it afterwards. Okay, so let's come back to Geogebra. And let's see what that looks like, okay? So I'm going to again take the value which I want, which is x. I'm going to add or subtract the value of a, okay? And then I'm going to square it, okay? So at the moment, the value of a, the value of A, this one here, is 3 because I've got it set to 3 at the start here. So I'm basically looking at the graph y equals x plus 3 all squared. And that's the graph which appears over here in blue. Now this is really intriguing, okay, because you're happy that because I'm applying the transformation to the x first, then I'm doing the squaring, it should happen in the x direction. But is it in the direction that you think it should be? Okay, so because I'm adding the value, it ends up that I take the graph, which remember is my y equals x squared, that's my dotted graph, and I'm moving it, it appears to the left by 3. Now you think because A is positive, because I'm adding 3 to x, it should be to the right, right? Because positive is generally to the right. But in this case, by adding 3 to my x, I end up moving it to the left instead. Now let's see what happens if I change the value of x. Let's maybe change it, sorry, the value which I'm adding. Let's change the value which I'm adding to 5. So I do x plus 5 first, and then I square it. Can you see that I've basically moved the entire graph even further to the left by 5? Now let's see what happens if I make the value negative. Well, can you see if I make the value to say like negative 3, that I basically end up with x minus 3, and that means that I'm moving the graph to the right. I'm moving the graph to the right by 3. Okay, now that is really interesting. So if I just set this playing, the moment the value which isn't taking away and I'm moving it to the right. But if I make it positive, it means I'm moving it to the left. In other words, the thing to notice here is that I'm moving the graph in the opposite direction to what is intuitively making sense. So let's come back to my tablet and let's see what happens here. So I've basically just observed, if I want to do y equals x plus a all squared, so I'm adding the value of a first, okay? Then what that basically corresponds to is I'm taking the graph y equals x squared and I'm moving it to the left, okay? I'm moving it to the left by a. So that basically means that if I'm adding a before I square it, then I basically end up over here at negative a, all right? So in other words, this is going to be the graph y equals x plus a all squared, okay? Whereas if I do the opposite, if I take away a, okay, so if I take away the value of a, then what's basically going to happen is that I move the graph over here. Okay, so 1, 2, 3, 1, 2, 3. So I move the graph over here to the right. This is going to be the graph y equals x minus a all squared. Now this is intriguing, okay? So it's the opposite to what you think. With the graph before, okay, if we add on a, it makes sense we're moving it in the positive direction. If we're taking away a, it makes sense that we're moving it in the negative direction. But if we're doing it the other way round, if we're adding on the value first, then squaring it, it just so happens that we move it in the opposite direction to what we think, okay? So as an example then, I wonder if you can tell me where the vertex of this graph is going to be. So if I give you the graph y equals x plus 4 all squared, I wonder if you can tell me where is the vertex of this graph going to end up. Well, all right, let's first of all think about the transformation. You notice that I'm adding on 4 to the x before I square it. Okay, so in other words, I'm applying a plus 4 transformation, but I'm not doing it after I square it, which means it must be in the horizontal direction. Now just remember, intuition will tell you that you should be moving to the graph to the right by 4. That's what the positive 4 generally would mean. But not in this case. We've just seen it's the opposite of what you think it should be. So therefore, instead of moving it to the right by 4, we're going to be moving it to the left by 4. In other words, the vertex will also be shifted to the left, so it will move from 0, 0 to the right, to the left, to be ending up at negative 4, 0. Okay, so we'll end up at negative 4, 0. Now what about if we take the graph y equals x minus 10 all squared? Where's the vertex going to end up? So I wonder if you can take a couple of seconds and just think, where would the vertex end up here? Well, hopefully you have a look here and you see that we're taking away 10. Well, if we're taking away 10, that must mean, and we're taking away 10 to the x before we square it, so it must be in the horizontal direction. However, it's not in the direction we think it will be. Okay, so we think because it says negative, we move it to the left by 10. In fact, it's the opposite, we move it to the right by 10. So therefore, the vertex will also be moved to the right by 10, so it will end up at 10, 0. Okay, so hopefully that makes sense. Now, just to help you with this a little bit more, and in fact, I'm going to come back to my previous example that I was just doing up here with my vertical shift instead. If I want to find the vertex, just remember that the vertex, one easy way of finding the vertex in this case, because the vertex is either in the direction of the x-axis or the y-axis, I can find the x or y-intercept. So as an example, with our vertical shift, where we're moving it up or down, so in this case we're moving it up or we're moving it down, it means that my vertex is going to be on the y-axis, which means that I should be looking for the y-intercept. So just remember, to find the y-intercept, I need to set x equal to 0, because just remember the y-axis is the line x equals 0. So the y-axis is the line x equals 0. It's basically the line with all the x values just equal to 0. So if I just take these two examples down here, and if I set x to be 0, I should end up with the y-intercept, okay? So if I take this one here, if I set x to be 0, I get y equals 0 squared plus 4. That gives me y equals 4, okay? That's the reason why y equals 4, and I already know the value of x because I've set it to be 0, okay? If I do the next one, okay, if I set x to be 0, I take y equals, well, 0 squared, take away 15, that will give me y equals negative 15, okay? And that's how I get my negative 15 here, and I already know x is 0 because I've set it to be 0. Now, if I do the same thing here, I know that it's going to be a shift in the horizontal direction. In other words, the vertex is going to be the point where the parabola crosses through or touches the x-axis. So in this case, I'm looking for the x-intercept. Well, the x-intercept, in order to find it, I need to set y to be 0 this time. So just remember, to find the y-intercept, I set x to be 0. Okay, in order to find the x-intercept, I need to set y to be 0 instead. So let's do that down here, okay, because I know it's a horizontal shift, so therefore I need to find the x-intercept. So in order to do this, okay, I'm just going to set, in this case, y to be 0. Well, all right, let's do it with the first one. Let's do it with this one here. If I set y to be 0, I get x plus 4 all squared is equal to 0. Well, if I solve that equation, well, that means I need to square root both sides, so I get x plus 4 equals 0. Then I need to take away 4 from both sides, so therefore I get x equals negative 4. Well, that's where my negative 4 came from there. And likewise, I already know why, because I've set it to be 0. Okay? If I just show you with the next example down, I take this, I set y to be 0. So I take x minus 10 all squared, and I set y to be 0, so all that is equal to 0. And if I solve that, well, I square root both sides, add 10 to both sides, and I find that x is equal to 10. Hence, I get my x equals 10 there, and I know my y is already 0. Okay, so it makes sense. It's consistent, all right? Even though it's the with this one, it's the opposite of what you think it should be, it's still consistent and it still makes sense. Okay, so I said that there was also another way in which we can get a different set of parabolas. So we've just seen with shifting, okay? If I take my y equals x squared and add or subtract a particular value, I move the graph up or down. Whereas if I add or subtract my particular value before I square it, then I move it to the left or right. And you just remember in this case, it's the opposite of what you think it should be. So if it's adding on some particular value to x before you square it, it means you're moving it to the left. And if you're taking away some particular value to x before you square it, it means you're moving it to the right, okay? But you notice that's shifting. There were a couple of other ways that I said we can get a transformation. And the next one was a stretch, okay? So in other words, I can change the steepness of my graph, okay? So let's see what happens with a stretch then. So following a similar kind of idea to what we did with our linear graphs, the way in which we got a stretch, the way in which we changed the steepness of a graph was by multiplying by some particular value. So let's see the same thing happening here with GeoGebra then. So again, I've got my dotted graph, which is y equals x squared, okay? And this time I'm going to see what happens if I multiply by some particular value. So for example, let's take a times by x squared, okay? So you can see now that because my value of a, you can see up here is 2, you can see that my graph now has basically been made twice as steep as what it was before, okay? So it's almost like somebody grabbed my graph and pulled it upwards so it's even skinnier. It's now twice as it's now skinnier than it was before, twice as steep as it was before, okay? And again, I can change my value of a, so I can make it 3 times steeper, or 3.5, or 4 or 5 times steeper, and you can see the graph is even steeper still, okay? And I can make that even shallower as well by putting it like, if I put it like a half, it means that now it's almost like I'm making it half as steep, so it's a bit like squashing it downwards by half. okay? And I can even make it smaller still. So like 0.1, it's more fat, all right? So basically I've just seen that with stretching graphs, the idea is that I'm literally just making the value of A steeper. So for example, that graph there, so it's not a great drawing, I know, but that graph there would be like y equals ax squared. I'm simply taking my original graph, y equals x squared, and multiplying it by some particular value, okay? And if I want to make it fatter, then again I can do the same, but just making sure that the value of A is less than 1, okay? So y equals, again, something like ax squared, but I'm just making it a bit shorter, okay? So that'd be like 1 over A as an example, okay? So that'd be like a half or a third or a fifth, okay? So if I want to stretch it upwards, so stretch it upwards, I just multiply by A. If I want to make it shallower, again, I just divide by A instead. Okay, so hopefully that makes sense. So with stretching, I can basically change the steepness of the graph, but you notice that in each of these cases, the vertex, okay, so remember the turning point of the graph, doesn't change, okay? So as an example, if I take the graph y equals 3x squared, okay, what this would mean is that actually the vertex would still stay at the origin. Because all it would mean is I'm just taking the graph and I'm making it 3 times steeper. I'm stretching it upwards in the y direction by 3. But the vertex doesn't change, it still stays centered around that origin point. If I take something like y equals a half x squared, again, all that's happening here is it's almost like I'm squashing it down, so it's half as big as what it was before, and the vertex would still be at 0, 0. Okay, so I'm not changing the vertex at all, okay? So that's stretching, and we've just looked at shifting and things like that. So there's one other way which I can transform my parabola to get a brand new one, and that's by reflecting it or by flipping it, okay? So if I take the graph y equals x squared, and if I try something like y equals negative x squared, let's see what happens. Well, if I come back to Geogebra, at the moment I've got my value of A, the thing which I'm multiplying by is positive, it's 0.1. But if I make it negative, can you see that effectively what's happening now is that I get exactly the same graph as above, but it's just being reflected in the y-axis. So basically, if the thing which I'm multiplying by out the front is negative, it basically means that I'm just making it, still having the stretch happening, but it's just happening in the other direction. It's almost like the x-axis is a mirror image. Okay, so as long as it's negative, it's basically being flipped over. Okay, so y equals negative x squared will effectively be a sad face instead of a happy face. This would be y equals negative x squared, and the original one was y equals positive x squared. Okay, so now we've looked at all of the 3 components together. Okay, we've looked at, first of all, a shift. Actually, before we do that, just a quick point. You notice with y equals negative x squared, the vertex is still the same. It's the same situation with a stretch, okay? So you notice when I stretch things, it doesn't actually change the vertex as such, okay? As long as it's centered at the origin originally, okay? So let's actually just do a quick summary. So the first thing we looked at was shifting, okay? And there's 2 types of shifts that we can have. We can either have it moving up or down. Okay, so remember, to move the graph up or down, we need to do y equals x squared, and then we need to either add A or y equals x squared, and we need to take away A. And that will basically move the vertex to 0 A if it's moving upwards, or 0 negative A if it's moving downwards. Okay, so that's the vertical one, that's moving the graph up or down. If we want to move the graph left or right, then we basically need to add or subtract the value of A before we square it. So if I do x plus A all squared, okay, then that would basically move the vertex. Now just remember here, because I'm adding A before I square it, okay, it's the opposite of what I think it should be. So it's a horizontal shift, but instead of moving it to the right, which you think the plus A should be doing, it's actually moving it to the left. Okay, so it's moving it to negative A, 0, like so. And likewise, if I subtracted A, so y equals x minus A all squared, then the vertex would move to A0. Okay, so it's moving it to the right and setting it to the left. So that's a shift, okay? So we can basically move the graph around either vertically or to the left, or horizontally to the left and right, just by adding or subtracting a value of A. And where we add or subtract that value is all about what type of shift it is, whether it's vertical or whether it is horizontal. Now the second type of transformation we looked at was a stretch, okay? So we could basically make the graph taller or skinnier. Okay, so taller or skinnier or fatter, okay? And the way which we did that was simply just by taking x squared and multiplying it by some particular value. Now, the really important point here is that actually the vertex doesn't change. So V for vertex, the vertex doesn't change. So it's still at the origin, okay? And even if we try dividing by some value, so that's going to be 1 over a times x squared, okay, then again, the vertex doesn't change. The vertex still remains at the origin like so, okay? And the last type which we saw was actually a flip or a reflection, okay? So we saw that when we flipped the graph around, for example, y equals negative x squared, then in this case, again, the vertex doesn't change, okay? So it's still at 0, 0. Again, why are we interested in the vertex? Well, the vertex is the turning point of the graph. It's literally where the line of symmetry is. It's literally where if we fold the graph in half, we get the same thing on the left as we do on the right. And it's also where the graph goes from positive to negative or vice versa, okay? So the vertex is a really important feature of trying to identify what is happening with this parabola. Now, at the moment, I've looked at each of these transformations kind of on their own, okay? So I've looked at like adding 4 or taking away 4 or multiplying by 3. But let's see what happens if I take a graph with multiple transformations that have been applied. That is totally fine, right? So if I take a graph something like this, if I take a graph like y equals x plus 4 all squared minus 3. Okay, so there's two things which have happened here. Let's first of all break it down. Let's first of all start with the x and let's see what we get if we start with the x. So the first thing that we would do using order of operations if we started with x is add 4. So you notice that we need to consider this part first. Okay, so we need to consider this part first. Well, we know, so ignore the minus 3, we know that if we had y equals x plus 4 all squared, that would be a horizontal shift, but it would be a horizontal shift to the left by 4. Okay, so in other words, the vertex would end up at negative 4, 0. However, there is also another transformation that is being applied here. We've also got the take away 3. Well, because the take away 3 is happening after we've squared it, that would correspond to moving down by 3. Okay, that makes sense. If I gave you y equals x squared minus 3, you'd say, I've just simply moved it down by 3. So because I've already established that that part there just moves it to the left by 4, the minus 3 must still move it down by 3. So therefore, the vertex is going to be negative 4, negative 3, like so. Okay. What about if I gave you something like this? What about if I gave you y equals 2x squared plus 5? Where would the vertex end up? Well, let's think first of all. Let's start with the x, okay? So we'll have the x, we'll square it first. The next thing that we would do is do the times by 2. So ignore the plus 5. If I just gave you y equals 2x squared. Well, in this case, it would just simply be a stretch in the vertical direction, so it would make it twice as big as it was before. And the vertex wouldn't change, okay? You happy with that? So the vertex would still stay at 0, 0. But now I need to consider what the effect of adding 5 is. Well, what if it was y equals x squared plus 5? You'd say you just move the graph up by 5, okay? So it's the same thing here. Because I start with the vertex at 0, 0 for y equals 2x squared, if I just add 5 to it, it's the same thing. I just simply move the vertex up by 5. In other words, it's going to end up at 0, 5. What about if I gave you something like this? Y equals negative x minus 1 all squared minus 2. Okay, well, let's have a think first of all. Let's have a think. So I'm actually going to draw this out in stages. First of all, I'm going to think what happens when I take away 1 first, because I always start with the x, then I think what happens. So first of all, I'm going to consider the graph y equals x minus 1 all squared. Okay, well, that graph would simply be moving the original y equals x squared graph, which remember has the vertex at the origin, and it would move it to the right by 1. So in other words, this graph is going to be over here instead. So it's going to have the vertex at 1, 0. So the vertex will be 1, 0. Okay. Then what's next going to happen? Well, the next thing that's going to happen is I'm going to consider multiplying that by a negative. Okay. So the next thing which I'm going to have to consider is that negative. So y equals negative x minus 1 all squared. Well, just remember, the act of putting the negative at the front is just simply a reflection. Okay, and it's a reflection in the x-axis. So therefore, I'm going to take the graph which I just had, which is this graph here, which had the vertex, oops, let's make sure it sits on the axis, which has the vertex at 1, 0, and I'm just reflecting it in the x-axis. So in other words, it would end up down here. But you notice that the vertex hasn't changed. So the vertex is still at 1, 0, okay? Then the last thing which I need to consider is the -2. Well, if I have y equals x squared minus 2, you just move it down by 2. Same thing here. It just simply means take whatever I've already got and just move it down by 2. So in other words, my graph now, so y equals negative x minus 1 all squared, take away 2, my graph now will just simply be down here. Okay, I'll just simply take this green graph and I just move it down by 2. So in fact, I should probably do that in green. So therefore, my vertex is going to be at 1, negative 2. Okay, like so. So therefore, the vertex of this graph is going to be at 1, negative 2. Okay, does that make sense? So we've looked at one really important feature of a parabola. We've looked at the vertex, and we've understood that just by applying different transformations, we can get to different, sort of different parabolas, and we can create a whole family of parabolas just by applying three things: a shift, either vertical or horizontal, a stretch, and then a reflection. So just by doing one of these three things, or combinations of these three things, we can get different families of parabolas, okay? So now let's have a look at something really important called the intercepts of the graph. Because the whole point is, what I'm trying to do here is build up all the skills that we need in order to draw this graph, okay? So if I give you something like y equals x plus 3 all squared, take away 4. Now first things first, can you tell me where the vertex of this parabola is going to be? Okay, so the vertex of this parabola, where is it going to be? Can I give you kind of 2 seconds just to think? Where's the vertex of this parabola going to be? Well, hopefully you've seen this. Let's break it down first of all. First of all, I need to consider the x plus 3 all squared. That's going to move the graph to the left by 3, so it's going to end up at negative 3. Okay, but then I do the minus 4, which means it's going to move the graph down by 4, so the y value is going to be negative 4. So that there is going to be the vertex of this particular parabola. But if I sketch it, okay, so if I sketch this, so I basically started off with y equals x squared. So y equals x squared is here. I've moved it to the left by 3. Okay, so I've moved it to the left by 3, so it'll end up at negative 3. And then I've moved it down by 4. Okay, so it's going to end up down here at negative 4. So in other words, my new graph is going to be here in green. So it's going to be something that looks like that. But are you happy that it actually is going to cross the graph, cross the axes? Okay, so it's going to cross the axes here, it's going to cross the axes here, and it's also going to cross the axes up here. So if I get rid of everything else now, if I get rid of that, we don't even need the original y equals x squared graph on there. There's 3 points which it crosses the x-axis. It crosses here, it crosses here, and it crosses here. So it crosses the x-axis twice and it crosses the y-axis once. I'm now interested, if I want to sketch this graph, now I know that the vertex is down here at negative 3, negative 4. If I want to properly and accurately sketch this graph, I want to find the location of these 3 intercepts. Okay, so I want to find the location of these 3 intercepts. Well, in order to do that, I can just rely on the fact that I know how to find the x and y intercepts. I just set something equal to 0. So let's first of all go for the y-intercept. Let's first of all go for this thing up here. So just remember, to find the y-intercept, okay, what I need to do first of all is set x equal to 0. So if I take this graph, y equals x plus 3 all squared minus 4, and if I set x to be 0, let's see what I get. So, okay, I get y equals, well, I've got 0 plus 3, so that's going to be 0 plus 3, because x is 0 now, minus 4. So 0 plus 3 is 3, square it, get 9, take away 4, that's going to give me 5, okay? So that's going to give me 5 there. So that's exactly what I want. So in other words, I know that this point where it goes through the y-axis, the y-intercept is going to be at 5, or if you prefer 0, 5, it doesn't matter which. Okay. But then I've also got the x-intercepts. I've got this intercept down here and this x-intercept down here. If I want to find the x-intercepts, just remember, to find the x-intercepts, I need to set, you guessed it, y to be 0. So let's do that. Let's take the original graph, y equals x plus 3 all squared, take away 4, and let's set y to be 0. So x plus 3 all squared, take away 4, and I'm going to set y to be 0. Now you notice that if I set y to be 0, technically I should have 0 equals x plus 3 all squared minus 4. I just prefer to write my equations so that it's equal to a number on the right hand side and the unknown is on the left. So I've just simply still set y to be 0, it's just I've swapped the sides around. Now in order to solve this, I guess we should add 4 to both sides. Okay, so if I add 4 to both sides, I get that, so x plus 3 all squared, remember, equals 4. Then I need to square root both sides. Now this is where we need to be careful, because if I square root both sides, you're absolutely right, square root of 4 is 2, but it could also be negative 2 as well, because if I take negative 2 and I square that, I also get 4. So therefore I get x plus 3 equals plus or minus 2. And then in order to solve this, I need to take away 3 from both sides. So I should end up with x is equal to negative 3 plus or minus 2. Now the way to interpret this is, first of all, I take negative 3 and I add 2, see what I get. Then I take negative 3 and I take away 2 and see what I get. So let's see. If I take negative 3 and add 2, well, negative 3 add 2, that's negative 1. So that's one of my values. This is one of my x-intercepts. And the other x-intercepts, what happens if I take negative 3 and take away 2? Well, negative 3 take away negative 2, that's going to give me negative 5. So here are my two x-intercepts. One is over here at negative 5 and one is over here at negative 1. Okay, so those are my two x-intercepts as well. So this would be how I draw this graph. First of all, I find my vertex. Okay, so I find my vertex just by thinking about the transformations that have been applied. Then I find my y-intercept by setting x to be 0. Then I find my x-intercepts by setting y to be 0. Okay, so just remember, you need to plot 3 kind of characteristics on this graph. The first is a vertex. The second is the y-intercept. The third are the x-intercepts. Okay, so there's 2 of them. Okay, so hopefully that makes sense. Now, ordinarily, that would be it. Okay, that would be all the quadratics finished. Everything I've just gone through in the last hour, that's all the quadratics finished. However, the unfortunate thing is that this here is not usually the form that we get given it in. Okay, so this here we would call vertex form. The other form that we could call it is completed square form. Okay, so completed square form. So if we see a parabola or see a quadratic written in this form, okay, or something like this form where we have some value squared, some value plus or minus a all squared, might times it by a particular value, might make it negative, then we add or subtract some particular value. This will be completed square form. So more generally, we could write this as some value times by x plus another value all squared plus another value if we like. And of course, the reason why I say plus b is because b could also be negative, which would make that a minus b, and the same with c as well, and the same with a. Okay, so this would be called completed square form. Now, unfortunately, as nice as it would be, we're not always given a quadratic in this form, okay? Usually we're giving it in general form or expanded form. So what I mean by that, if I take this thing here, if I try to expand this, in other words, having x plus 3 all squared, let's see what happens if I expand this. Well, I could write that as x plus 3 times x plus 3. And of course, I'm going to have to take away 4. Instead of writing it squared, just written x plus 3 times x plus 3. Okay, so no drama so far. Then if I expand this out, and we have had practice of expanding this out, I would have x times x, which is x squared, then x times 3, which is 3x, then another x times 3, which is another 3x, and then 3 times 3, which is 9, then finally take away 4. So after I tidy all this up, I would get x squared plus, well, 3x plus 3x is 6x, and then 9 take away 4, that's going to give me positive 5. So in other words, this y equals x plus 3 all squared minus 4 could also be written as y equals x squared plus 6x plus 5. Okay. Now if you see it written in this form, we would call this expanded form or general form. Okay, so if you see it written like this, and unfortunately, we usually see it written like this an awful lot. Now, this is called general form. So in other words, if you see it written as y equals some value times x squared plus another value times x plus another value hanging around at the end, we would call that general form. Now, the unfortunate thing about general form, at least for us anyway, is you see, if I give you y equals x squared plus 6x plus 5, it's very hard to relate that to the graph that we've drawn up there. Like, okay, well fine, where is the vertex from that? How do we get the vertex from y equals x squared plus 6x plus 5? How do we get the x intercepts? How do we get the y intercepts? So it's much harder to extract that information in general form. But unfortunately, that's how we generally tend to find it, okay? So what we're going to look at from now on are techniques which we can use to work with general form to still be able to pick up the important features of a quadratic, namely the vertex, namely the intercepts on the y and the x-axis. So what are the important features of the parabola? And we're going to look at how we can convert general form and how we can deal with general form and still get those important features back.